Okay, hello, my name is Frank Boxberger. Welcome to notes7.com. Of course, that's our web address. This is Notes 7 Creative Engineering. Again, I'm Frank Boxberger. I'll be teaching this class. This is the first one. If you have any questions, comments, anything, notes7school@gmail.com. Email me and we'll answer any questions you have. So every single lesson, this being the first, we're going to start off with a riddle. We're not going to tell you the answer to the riddle. That's where you have to email it in. If you get something, the right answer, we'll let you know. If you get a creative answer, maybe more right than what we're even expecting, we'll let you know. We want you to be creative with these answers. If you want to know the answer, you can't figure it out, email us. We'll let you know that too. Anybody that actually gets the answer will post online later. Super creative answer, we'll post that too. So the first thing is riddle of the day. We have the earth. Okay? Now, on riddles and all of our mathematical equations, scientific equations, we're going to come up with assumptions to make things easier to understand. So, even though I didn't draw a perfect sphere, we're going to assume this is the earth, and we're going to assume it's a perfect sphere, which means this would be a perfect circle. Okay? This is the earth, perfect sphere. Now, around the circumference of the earth, it's 24,901 miles. So we've got 24,901 miles around a perfect sphere. So the riddle is, if you took a string, I probably should do this a different color. If you took a string and put it on the face of the earth all the way around and touched it end to end, so it's laying on the earth all the way around, perfect sphere, and it touches. Again, second assumption, the string has no elasticity, so it does not stretch. So it touches end to end, so the string is exactly 24,901 miles. Now you guys probably know 1 mile is 5,280 feet, okay? So this is an amazing distance. Well, so of the 24,901 miles, we're going to add 6 feet, not 6 miles, 6 feet of string. So an infinitesimal amount of string. We're going to add that to it. I'm going to exaggerate here. So as we add that extra 6 feet of string here, it's going to create some slack. So the riddle simply is, if you could now spread this string equal distance away from the earth, what is the distance equally this will be spread around the face of the earth? So how far off the earth's face will the string be? And the answer will surprise you. That's the riddle. We're done with that now. You can rewind and play it again if you have questions about it. 24,901 miles. The outside string, 24,901 miles plus 6 feet. That's it. What's this distance? Okay, so on to the buoyancy principle. That's the title of today's lesson. And in this class, we want to do fun things. So today we're going to figure out what Archimedes' buoyancy principle is, how it actually applies in the real world. So by the end of the class, we're going to actually design a paddleboard that will support your weight individually. And you can make it any size you want. We'll probably, for the purposes of this, assume a 3-inch styrofoam type of material. And we'll also assume that we only want the water to come up 2 inches above the styrofoam, leaving us 1 foot as we stand on it above surface. So start with Archimedes' buoyancy principle. So this is water, okay? And the principle is for any ship, boat, paddleboard, whatever is floating in water, it will, if it floats, it will have a distance that it submerges into the water. Okay, it turns out this submersion distance, I'll call it ds, is critical. So the buoyancy principle is simply, we take the volume of, and of course this has some kind of a depth to it too, okay? So we take the volume of this craft, ship, whatever it is, that's underwater. So depth, width, length, and multiply that times the weight of the water. That's the exact same weight as the ship. So that's pretty cool. I don't know if you got that. So it's fantastic. The weight of the water we'll call gamma, and gamma is just a Greek letter for, a lot of times it's for density. So the density of salt water is 64.4. I wrote that to here. If you're freshwater, it's 62.4. But we're going to do paddleboarding in the ocean or sea, so we're going to use the density of water. So we simply, to calculate the weight of the ship, and you can have gold sitting in it, you can have stuff above ground, the mast, the sail, people standing on it. We will know exactly by how much it sinks, because the greater the weight, the more it'll push down under the water surface. So for instance, in this particular exercise, let's say this area is this is 3 feet into the water. Even though the ship might be 5, 6, or 7, this distance doesn't matter. We'll say this ship is 3 feet wide, and we'll say it's only 3 feet deep. So we have length 3 feet deep. This is the portion underwater. So 3 times 3 times 3, that equals 27. So that's we always got to carry units, feet, feet, feet. So that's feet cubed. Okay, so that's how much of the volume is underwater. We simply multiply that times then the weight of the water, which we called gamma, and that's pounds per cubic foot. Okay, now a lot of times when one's above and one's below, you cross those out. So you take 27 times 64.4, and that now is how many pounds the ship weighs. Okay, unfortunately, I don't have my calculator, but it's 27 times 64.4 equals, you can put it in your calculator, that's the pounds this craft weighs. If I put another 1,000 pounds on it, it would sink. This number would get greater, increase that, and we would have a different answer. So as the ship increases, whether it's the thickness of the material, it doesn't matter, because that adds to the weight, what's inside, what's on top. So it's so cool. It's the weight of the ship, it's the weight of the gold or silver inside, the weight of the people, everything can be calculated simply by the displacement of the water, as long as you know the weight of the water, which I just told you. Okay, so now we're going to use that principle. This is the application. We're going to use that principle now. We're going to design you a paddleboard. So in my case, let's say I weigh 170. It's probably really 175, but 170. We're just going to assume that the paddleboard weighs 10 pounds. So we're going to design a craft for me that will hold 180 pounds. This is a craft, in this case a paddleboard. So the weight we need to hold is 180 pounds. Okay, and that can be lb or a pound sign. Different symbols a lot of times are used for different units. So the units is pounds, the weight 180. So now what we need to do, we also know the gamma. We're doing this for salt water. I want to do this in the ocean, put a paddleboard. We know that's 64.4. Okay, and that's, again, units are important. That's pounds per cubic foot. Okay, so then this is our formula, but in this case, we want to solve for the volume. In this case, force and weight are the same thing. So then what we do, we want volume, so we just take this divided over here. So volume equals force, or W, my weight, we'll say in this case, or it could be force, divided by gamma. So the volume of the craft we need to make for me is so easy. It's my weight, W, 180 pounds, divided by the known, the salt water, 64.4. And that's pounds per cubic foot. One of the best things you can do is carry units, because then you always know those cross out, this goes to the top. And so now, basically, we got 2, this is to the third, 2.8, okay, cubic feet. So now my craft, in this case a hunk of styrofoam, needs to be this 2.8 feet in volume. And so that will completely float me. So what we're going to do, even though we are going to make a 3-inch board, I only want the water to go under by 2 inches. So we're going to take 2 inches, which really you have to divide that by 12 to get to feet. So 2 inches is what I want the board thickness. Now I get to say, do I want it 20 inches wide, 24 inches wide? I decide the width. In this case, I'm going to say 24 inches wide just because it's simple math. So this is in feet because 2 inches divided by 12. Then I want it 24 inches wide, which is 2 feet, okay? And then the unknown, so we'll put X, that's the length. So the length is the only thing that we need to know. In fact, we'll just call it L. That's the length I need to know when I cut my 2 inch by 2 feet wide, 2 inch high, 2 feet wide. What length do I need to make so that when I stand at it, it only sinks 2 feet? Well, the other known is we know the 2.8 feet. Okay, so now you do the math. The length of the board is what we need to know. L equals 2.8 cubic feet divided by the way, this number and this number, so you divide it by 2. You also divide it by whatever this is. We can say 2/12, or actually you can bring the 12 to the top, and it turns out that it is 8.4 feet. So I made it more complicated. It's really very simple. So you just plug your weight in. This includes the board. My weight 170, 10-pound board. I need to make it 8.4 feet. Now if I go cut out a piece of styrofoam that is 2 feet wide, I'm going to cut it at 3 inches because 1 inch will always be showing when I'm on it. So you don't want to make it exactly your height, or as soon as somebody jumps on it like your dog, it sinks. In this case, styrofoam wouldn't sink, but a ship would. And then we make it 8.4 feet. When I get on it, it sinks down 2 inches, and voila, you have your paddleboard. Okay, that's it for today's class. Again, if you enjoyed the class or didn't enjoy it, let me know. Maybe we can do something different. notes7@gmail.com, and notes7.com is the website. All our classes are on there, other fun things that you can explore, some of my theories, some of the music that we're producing, and that's really it for today. Thank you for joining us. Again, my name is Frank Boxberger, Notes 7 Creative Engineering. Thanks. Bye.